Hey guys, welcome back. Steve here with 6 Automotive. Moving on to the next video in our scope series, we're going to go over a test that's really fast, really easy, and can give you a lot of extremely useful information. But before we get started, like, subscribe, and join me as we go over relative compression. So a relative compression test is extremely useful and something every tech should have in the toolbox. There are a couple of tools that you're going to need in order to get this done. Just like every video so far, you're going to need some sort of a lab scope. In this case, we're going to stick with the U scope, but you're also going to need a high amp probe. This one is a 0 to 600 amp. A 0 to 200 amp can give you a bit more definition, considering most passenger cars aren't going to pull anywhere near 200 amps when they're starting. That way you get a bit more definition out of your waveform, but this, as you'll see, will do the trick. This one's from AES Wave, probably not too expensive. It's from these guys. These guys are so great. So kind of like the low amp probe, when we did the amp ramp on the ignition coil, the high amp probe does have power. I killed the battery when I was getting ready for this video. Make sure you turn it on, and you're going to connect it to your main negative cable. In this case, we're going to do it right here. Really doesn't matter. In this case, I'm going on the main negative. Just like the last one that we did, these are polarity sensitive, so might have to kind of fidget with it to get the reading to be positive. So you need to look through your fuses and make sure that you cut out fuel. Whether you yank a fuel pump relay, or in this case I pulled the fuel pump fuse, but we don't want any fuel to be dumping in here. You need to be able to crank it and not have it fire. Just disabling the ignition is not the best idea, because then you're still putting fuel in and you could wash out your cylinders, get weird results, and flood. Forget all that. Just stop the fuel. You should be able to figure out how to get the vehicle to crank and not start. Find a way to make that happen. So based on what your probe says, in this one, 1 millivolt is 1 amp. So if you have an idea that 100 amps, roughly 120 amps is probably going to be your high spike, or the highest that the starter is going to draw, then you can do your math on your volts per division. So if you do what, 20 volts per division, let's see what it looks like here. We're going to look at our scope. We're going to see that our maximum is 14 volts. That's totally not going to work. So let's drop this down, and we want our maximum to be, there's 350 millivolts, which is 350 amps, and now we got 140 millivolts. So we're at the 20 millivolt scale down here, and that should do us just fine. And we're going to look at, what, 5 milliseconds to, no, we're going to need to see this. You know, we're cranking, right? So yeah, this should probably be about good enough. Let's crank it and see what it looks like. All right, so let's take a look at the waveform. What are we actually seeing here? So what we're looking at is the current that's going through the battery while we're cranking. So we're monitoring the electromagnetic field around the wire to determine how much amperage is going through the wire, and then that tells us how much load is on the starter, and then that tells us how much compression is in the engine. At least relatively, which is why it's called the relative compression test. So we don't know what the compression is specifically, but we can tell what it is compared to the other cylinders. So if it's the same, then they're the same, which is what compression is all about anyway, right? Within a 5 to 10% margin of each other. So when we start our relative compression test, you're going to crank the car, you'll see an initial spike, which is that starter ramping up and getting the engine started. Just like when we have that KV spike we were just talking about in the last video, it's difficult to get things moving, but once they're moving, it's a lot easier. So you'll have that initial spike, getting the boulder moving, and then you got back to that very even line, ideally, of the bumps from every individual cylinder resisting the starter's movement, which makes the starter have to draw more current in order to push past that. So it should go compression down, compression down, compression down, compression down, compression down, and that tells us how strong the engine's health is. You have to have a strong battery in order to do this. Don't try to do this on a dead battery, obviously. So what would a bad waveform look like? I mean, as you can see here, this is what a good waveform looks like. A bad waveform is going to have a dip in one of these guys, so they're not going to be as even as this one is. You'll see even down, even down, even down, right? And so if you have a test that's not good, you're going to need some sort of another channel in order to figure out which one that is. I'm using this as a justification for a compression test. So if I find one wrong, I'm not really too concerned right now anyway about which cylinder it is, just that there's something potentially mechanically wrong. So you'll need that second channel in order to sync the firing order. So if you put a secondary ignition like the Wise probe on one, like cylinder 2 or whatever it is, and then you can, and you know the firing order, which you can easily look up, you can go 1 3 4 2 1 3 4 2, and you know that you have a clamp on cylinder 2, so then you can just count off from there. Okay, that's cylinder 3, and every time cylinder 3 hits, that's the one I'm going to go after testing cylinder 3. So when you're doing this test, you want to make sure you crank long enough, about 3 or 5 seconds or so, to let the engine kind of get into that stable rhythm. You know, I mean, don't just crank, and that's it. Obviously, as you can see from the test, you're going to get really big spike, and then, but you need to let it do the big spike and then start to kind of even out and do its compression, and then take your readings from that number. So an important thing to note is when you're using the oscilloscope, you can pause the screen where it is and hold it with the A button, or you can hit the B button to capture. So I'm not exactly sure how the capture thing works yet. I haven't used it. I almost forgot. So what are the downsides of the relative compression test? So you're not going to get any specific PSI readings. It's about how the cylinders react relative to each other, not about what the cylinders are individually. So if you have something really minimal, like a valve that's only slightly leaking, so like it has a really kind of a slight misfire at cruise or something weird like that, and you end up having a misfire, relative compression is not going to find really tiny problems. Also, another thing is running compression. So a relative compression isn't going to work when you need to do a running compression test. So if you need to understand why you need to do that, we can do a video on that. But running compression test is really important, and if you need to do that, this isn't really going to help you there. So like I was saying a little while ago, you're doing the relative compression test to justify or not justify a legitimate compression leak down test. Thanks for watching, guys. I hope this one helps. And remember, if you're in the Sandpoint area, you can come by and experience a 6-star difference for yourself. Almost forgot. Make sure you turn this thing off